So you get X, and that is the concentration of H plus. So what do you do with that? You want to find pH and percent ionization. And pH is the easy one. Well, they're both pretty easy. The pH, I feel like we know the equation already. Negative log of H plus. And you plug it in your calculator. And then for percent ionization, it's a little bit more interesting. You're wondering how many of the H pluses are, how many of the atoms split up, basically. So this would be H plus at equilibrium over the CH3 COH initially. And you'll see for the strong acid that this is always 100%, which is what a strong acid, what it means to be a strong acid. And in this case, we have the H plus concentration over the initial, where is that initial constant? 0.1. And you get about 1%, 1.3%, looks like. So that's not too hard. What is part B? Part B is just the same thing but with less concentration. So same X is small approximation works, and you get different numbers, and that's it. The percent ionization changes, that is interesting. So when you have a different amount in there, then it ionizes, well, there's less in there. There's a lower concentration in there and more of it ionized. So that must be because it's, since fewer of the CH3COOH are in the solution, it's happier to split up. It's, that rule, the French-Caille rule. Le Chatelier, I believe. But that's, you can always calculate that. I don't think we need to know that as a general rule. But I would assume that is a general rule. Percent ionization goes up if concentration goes down. I'll have to ask Dr. Spencer. For C, you have strong acid, and so the ice table is quite easy. All of it ionizes. So look something like, space down a little bit. Let's see, HNO3 plus, or goes to H plus and NO3 minus. And so that's the reaction. The initial is all of it, whatever the initial concentration is. 0.1, yep. And then none, change, down, up, but it's all of it. So you don't even need to write X. You can just be like, we don't even need the change. Just be like, go straight to equilibrium. The equilibrium is none of this, and all of this, and all of this. Which I put the zero, didn't put the zero in the right place. But that's about it. So you do the K, and it's all products over no reactants, so that's infinity. which is what it is for any strong acid. It's unmeasurably high. That's why she didn't write the Ka over there either. Oh, well, she doesn't even write that calculation line, is what I mean. Because it's just huge Ka. So you do the pH, it's, let's see, the pH equals negative log 0.010, which, as it turns out, is 2. And, oh yeah, sig fig rules. I guess I haven't really talked about that. I'll go ahead and go back to the first one and talk about sig fig rules. Going into this, we have 2 sig figs, and pH has 2 decimal places. And so my little memory hint, so to speak, is you go between O, what are the things? There's H plus, there's pH, there's OH minus, or POH first of all, and then there's OH minus. And my little reminder is this is 1 point, just as an example. This is not universally true, but an example would be this is 1.0 times 10 to the power of negative 6 would go to pH being, this is not going to line up nicely. I'll space it out a little bit. pH is going to be, in that case, 6 because of that exponent, and that only works because this is 1, by the way. And POH is 8 because you use 14 minus 6, and the OH minus would be 1.0 times 10 to the power of negative 8. Oh, and right, the sig figs. That's the whole point that I'm trying to make here. Is that's going to be that 0.00, and that's going to be 0.00. And that's because decimal places here. There's 2 decimal places. 2 decimal places, 2 decimal places, and that gives you 2 sig figs in the normal numbers. In the numbers that have units. Or concentrations is the better way to say it. So concentration, 2 decimals, 2 sig figs. pH, 2 decimals. That's about it for that. So anyway, that was just an example. I'm going to label that as such. Just an example. But I think for the HNO3, pretty much obvious. Percent ionization is 100 for all strong acids, because you plug in the final and the initial, and it's like I'll go ahead and show it. Percent ionization equals using my formula from above. The H plus at equilibrium over the, in this case, not CH3, so H, but the nitric acid. HNO3. Really. Yep, that's it. So, which is the same over the same. It's like 0.1 over 0.1, which is the same thing. And so it's 1, which is 100%. So for D, same idea, strong acid, nothing special. And the last 3, let's see, HClO is not a strong acid, but the exact same process as part A. And then this last one, is there anything special there? No, K is still really small, so that means you can still use the small x approximation. So pretty much it's all pretty straightforward. Next.